concavity. The first derivative, you remember, measures slope, which was the rate of change of the y value with respect to x. Well, concavity measures the change in the first derivative, because the second derivative measures the change in the first derivative, so it becomes the change in the slope, so how the slope changes. And as I say, that's what we call concavity. So if that second derivative is positive, that means the size of the slope is getting bigger and bigger. So it might start with a negative slope and become more positive. So it's negative, 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 0, positive, 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 positive. And so you end up with concave up, basically, is the concavity. So if the second derivative is negative, that means the size of the slope is getting more negative. So it starts positive. And then it's getting smaller and smaller and smaller. It gets 0, then negative, negative, negative. You end up with something that's concave down. Then, of course, there's always the possibility that there is no concavity at all. And that's what we call a possible point of inflection. We'll talk about inflections a little bit later. A very, very rough sketch we're going to draw here by purely looking at the second derivative and nothing else. So we've got our function, differentiate it once, get the first derivative, differentiate it twice, get the second derivative. So that's all I'm looking at. So at this stage, what can I use it for? Well, all I can really use it for is when is it concave up, when is it concave down? So I'm going to investigate when it's concave up. And again, explain what you're doing and you're working out. Why on earth am I investigating this? Well, I'm investigating this because I know the curve is concave up when the second derivative is greater than 0. So that's what I'm investigating. And that's when x is greater than minus 5 on 3. Logically then we would think, well, therefore it must be concave down when it's less than that. So I can draw a very rough sketch. There's my x value. So it must have that sort of shape. Now at this stage, because all I'm using is the second derivative, I don't know exactly where those turning points are and things like that. But at least I've got an idea of what the curve's doing, the actual shape itself. So that brings us then to, well, those turning points. We can now combine what we did with the first derivative with the second derivative to really identify these points a lot quicker. See, every turning point is a stationary point. We know that. So we can locate the possibilities by solving when is the first derivative equal to 0. And then we go and investigate that point. What happens with the second derivative? Well, if it's concave up, well, think about it. Use your arms if you like. Concave up. Where's the stationary point? Here I am, down the bottom. So it must be a minimum turning point if I have those two conditions. If it's concave down, arms go down. Here I am at the top. Got to be a maximum turning point. So again, using the two pieces of information, we can get a much better picture of what's happening. So let's find the turning points of this one. Okay, first derivative, second derivative. So we're going to locate the turning points, or the stationary points. Again, explain what you're doing. Stationary points occur when the first derivative is equal to 0. This is why we're solving this equation. We've got a quadratic. Turns out to be x equals a third or x equals minus 1. Now previously we would then draw up a table of values and check either side. But now we can use the second derivative to do it a lot quicker. When x equals negative 1, let's investigate. What's the second derivative? The actual number probably isn't that important. Really what we need to know is it positive or is it negative? Well, negative 4, that's telling me the curve is concave down. So therefore, minus 1, 2 must be a maximum turning point. Let's check the other one. Sub that in, I get positive 4. So we know that one's concave up. We must have a minimum turning point. So the table of values, when do we use that? It's still a useful tool. Because if you get a function that's tricky to differentiate, then it's probably going to be tricky to differentiate it a second time as well. So it might be quicker just to test either side of the first derivative rather than worrying about trying to differentiate a second one. But something like a simple polynomial, always going to be easy to differentiate. So it's going to be a lot easier. Okay, so these inflection points then, that's where concavity changes. So there's no concavity at that point. It will change from concave up or concave down, maybe. So that's why we're finding possible inflection points. They might not be inflection points, but we're checking concavity to see what it is. Cubic. Let's find any inflection points it might have. So we'll need first derivative, second derivative. I'm going to locate possible points of inflection. Can't stress that word enough. Possible. Doesn't mean they are. They're possibilities. So we solve the second derivative and we get x equals minus a half. We need to check either side to see whether concavity changes. So draw up my table of values. So negative a half is where we're investigating. It has no concavity at that point. Okay, we need to pick a point on the left, point on the right. Same rules apply. Don't go past any other, in this case, possible inflection point, or don't cross any asymptotes when you're picking your number. So what did I pick? Negative 1. Sub that in, I get negative 12, so it's concave down at that point. Pick one on the right-hand side. Well, 0 is always easy to substitute in. Positive 12, concave up. So I can see, yes, indeed, there is a change in concavity. Make sure you write that conclusion down. Yes, there is a change in concavity. Remember, that was what we're investigating. So you write your conclusion down. I've discovered it has a change in concavity. So therefore, it is indeed a point of inflection. Now, polynomials, logically it's going to be, because polynomials are continuous curves. So if it's continuous and you know you've got a maximum point and a minimum point, there must be an inflection point somewhere in the middle. All cubics, all odd-powered ones for that matter, will have at least one inflection point. There's a special type of inflection point known as a horizontal point of inflection. And that's what we see in our basic cubic there. We have a point of inflection, it's change in concavity. But not only is it a point of inflection, it's a stationary point as well. If you were to draw a tangent at that point, it would be horizontal. So all the conditions for a horizontal point of inflection has to be a stationary point. So we know the first derivative is equal to 0. It has to be a possible point of inflection. So we know the second derivative is equal to 0. And there must be a change in concavity. Therefore, the third derivative is not equal to 0. The third derivative? What? Let me explain. There is an alternative way of finding inflection points. Now, we would find our possible points of inflection. But just like we did going from the first derivative to the second derivative, instead of drawing the table of values, we said, well, I'm going to use the second derivative because that tells me where there's a change in slope. Well, logically, the third derivative must tell you if there's a change in concavity. That's why we can use the third derivative. In fact, the actual rule is this. If the first non-zero derivative is of odd order, so the first time you substitute the possibility in and it comes up not being 0 as the answer, then that's a point of inflection. Now, the vast majority of things we look at, it's the third derivative. But if it wasn't the third derivative, you just keep going until you get one of these derivatives not equaling 0. If it's odd, you have a point of inflection. If it's even, then you don't have a point of inflection. So for our example, how would I have done it? Well, remember I found the first derivative, the second derivative, and then the third. Now I'll find the third derivative. I would have done that. In this case, it's just a constant 24. I would have located my possibility, but at that possibility, the third derivative is 24. It's 24 everywhere. But 24 is not equal to 0. So there is a change. The size of the change is 24. I don't really care. I'm not just interested that there is a change. There is a number there other than 0. 0 would indicate there's not a change in concavity. So from there, I would still put that line in, and so therefore, it must be a point of inflection. So we'll do exercise 4E.